It's 2025, September 25th, if I'm not mistaken. Always forget the day. It's just, I take it for granted so much. Yeah, September 25th, approximately 12:28 p.m. And we're going to be continuing the section 1.6 exercises from Dummett and Foote with the Kikola solutions kept in mind, especially in mind, along with my own thoughts and opinions and intuitions and all that. So, without further ado, let's get back into it, going to the I thought we were finished with exercise 10. I believe we finished exercise 10, which means we can go on to exercise 11. Have I finished exercise 10? I'm gonna check. Yeah, I believe I finished exercise 10. All right, well, on to exercise 11 then. So, let A and B be groups. Prove that A cross B is isomorphic to B cross A. So, intuitively, it's like, well, just swap the coordinates, right? The map from the ordered pair A comma B to B comma A, B comma A clearly respects the product and has itself as inverse, right? So let's go about doing this a bit more rigorously. Okay, so first off, let's define the map. So let's let Phi, give up on the pronunciation, be the map A of A cross B to B cross A by phi of A comma B, which is equal to B comma A. Now for the homomorphism part, for A comma B and C comma D within A cross B, phi of A comma B and, well, times C comma D in this case, is equal to phi of AC comma BD, which is equal to BD comma AC, which is equal to BA times D comma C, B comma A times D comma C, which is equal to phi of A comma B times phi of C comma D. So that holds. So phi is a homomorphism. All right, on to the next one. Well, no, sorry. Clear the board, and then I've got to continue on with showing that it's actually bijective. So, we'll do this via explicit inverse. Define psi as the map from B cross A to A cross B by psi of B comma A being equal to A comma B. Then psi composed with psi of phi is equal to the identity of A cross B, and phi of psi is equal to the identity of B cross A. Hence, phi is a bijection with inverse psi, and so we conclude that A cross B is isomorphic to B cross A via the map from A comma B, I mean to say, to B comma A. Right? Very good. Let's go on to exercise 12. All right. Second, I've got to rearrange my attire real quick. Just realized I've been sitting here in uncomfortable mode. So, for exercise 12, let A, B, C be groups, and set G equal to A cross B, H equal to B cross C, and prove G cross C is isomorphic to A cross H. So intuitively, it's like, well, just regroup the parentheses, right? The map, open parentheses, so open parentheses, A comma B, close parentheses, C, close parentheses, to open parentheses, A comma, open parentheses, B comma, C, close parentheses. That's is the obvious sort of, well, it's not supremely obvious, but it is the coordinate shuffle we're looking for. It preserves component-wise multiplication and has an obvious inverse. So let's go ahead and show that a bit more rigorously. So define, let's start by defining the map. Define the map. So let's let phi be the map from G cross C to A cross H, be phi of open parentheses A comma B, close parentheses, comma C, close parentheses, which is equal to open parentheses A comma, open parentheses B comma C, close parentheses. Now so we've defined the map. Now let's discuss how this is a homomorphism. So for open parentheses, A1, comma, B1, close parentheses, comma, C1, okay, open parentheses, A sub 1, comma, B sub 1, close parentheses, comma, C sub 1, close parentheses, comma, open parentheses, A sub 2, comma, B sub 2, close parentheses, comma, C sub 2, contained within G cross C. We have phi of open parentheses A1, A sub 1, A sub 2, comma, B sub 1, B sub 2, close parentheses, comma, C sub 1, C sub 2. We have that is in fact equal to open parentheses A sub 1, A sub 2, comma, open parentheses B sub 1, B sub 2, comma, C sub 1, C sub 2, close parentheses, and we'll continue along here right after I erase the board. And that is in fact equal to open parentheses A sub 1, comma, open parentheses, B sub 1, C sub 1, yes, and close parentheses, open parentheses, A sub 2, comma, open parentheses, B sub 2, comma, C sub 2, close parentheses, which is equal to phi of open parentheses, A sub 1, comma, B sub 1, close parentheses, comma, C sub 1, close parentheses, times phi, of phi. So that phi times this phi, which gets you an overall tax of 9.8%. No, but phi of open parentheses, A sub 2, comma, B sub 2, close parentheses, comma, C sub 2, and that's what gets us our homomorphism. It's closed, it works, the operations work, so it's closed under the operation. Now let's move on to determining whether or not this thing is bijective. And we'll do that in this case using an explicit inverse. Ooh la la. No. Okay. It's a very explicit inverse, kids. Turn your eyes away from this. No. Okay. Define psi being the map from A cross H to G cross C by psi of A, comma, open parentheses, B, comma, C, close parentheses, is equal to open parentheses, A, comma, B, close parentheses, comma, C, close parentheses. Then psi composed with phi of open parentheses, A, comma, B, close parentheses, comma, C, that is in fact equal to psi of A, comma, open parentheses, B, comma, C, close parentheses, which is equal to open parentheses, A, comma, B, close parentheses, comma, C, close parentheses. And taking the other way, flipping these around, phi of psi of A, comma, open parentheses, B, comma, C, A, comma, open parentheses, B, comma, C, close parentheses, well, that is equal to phi of open parentheses, A, comma, B, close parentheses, comma, C, which is equal to open parentheses, A, comma, open parentheses, B, comma, C, close parentheses, close parentheses. So psi is equal to the inverse of phi, right? And therein we can conclude G cross C is isomorphic to A cross H, and this is via the map from open parentheses, A, comma, B, close parentheses, comma, C, close parentheses, to open parentheses, A, comma, open parentheses, B, comma, C, close parentheses, okay? Now let's move on to exercise 13. Right. In the 13th minute. Okay. Let G and H be groups. This one's out of ink. Okay. Can I actually make it to the trash can? That's a far off distance, man. I don't know. Okay, let G and H be groups, and let phi be the map from G to H be a homomorphism. And we have part A, prove that phi of g, which is equal to the set containing phi of g such that g is within g, is a subgroup of H. And for B, part B, prove that if phi is injective, then G is isomorphic to phi of G. Okay? Now, let's see. Okay, intuitively, images of homomorphisms are stable under the operation and inverses because phi respects multiplication and inversion. For B, we can restrict the codomain to phi of G. Then phi becomes a bijective homomorphism, aka also known as an isomorphism, right? So let's look at that more rigorously. Okay, so for part A, we want to see that phi of G is a subgroup of H. So, okay, let's look at the, let's look and see if this is actually the case. So, is it the case that this thing is non-empty? Well, phi of the identity of G is equal to the identity of H, which is contained in phi of G, right? So, yes, it is non-empty. Okay, now, how about closure? Does it have closure? Well, if A is equal to phi of alpha and B is equal to phi of beta lie in phi of G, then we have that AB is equal to phi of alpha times phi of beta is equal to phi of alpha times beta, which is also contained within phi of G. Okay, now let's take a look at inverses. So that demonstrates closure. Now let's look at inverses. Okay, so if A is equal to phi of alpha, which is contained in phi of G, then the inverse of A is equal to phi of the inverse of phi of alpha, which is equal to phi of the inverse of alpha, which is contained in phi of G. So we have our three big properties right there. We have that it's non-empty, we have that it's closed in the operation, we have inverses. So well, we also have the fact that it has the identity, right? That non-empty kind of coincides with, the identity part. The Born identity, the subgroup identity. Right, so phi of G is a subgroup of H. All right, and that kind of seals the deal there. Now let's move on to part B. All right, so for part B, we want to show that injectivity in this case, it's injective, so therefore we have an isomorphism on the image. Onto the image. Right, okay. So consider the same function with restricted codomain. So such that we have phi asterisk is equal to, well, is the map from G to phi of G, and phi asterisk of little g is equal to phi of little g. Now, this is a homomorphism, and is surjective. By definition, of phi of g. All right, so now let's take a step back, and then we'll see about bijective here in just a moment. Well, okay, we'll see about this entire thing in a moment. So, if phi is injective, then so is phi asterisk. So phi asterisk is a bijective homomorphism. Also known as an isomorphism. Ergo, G is isomorphic to phi of G. So, to conclude, phi of G is a subgroup of H, and phi injective, phi being injective, implies G is isomorphic to phi of G. Okay? Now let's move on to the next exercise. Get rid of this over here. Oop. Exercise 14, on to exercise 14. So, for exercise 14, let G and H be groups, and let phi be the map from G to H, be a homomorphism. Now, prove that the kernel of phi is a subgroup of G. Also, another part here, prove that phi is injective if and only if the kernel of phi is equal to the identity, is equal to the set containing 1, i.e. the kernel, that is, the kernel of phi is the identity of subgroup of the subgroup of G, of subgroup of G, okay? So let's think about this. So intuitively, the kernel is the pre-image of the identity. Homomorphisms preserve multiplication and inverses. So this set is automatically closed under the group law. For injectivity, two elements have the same image exactly when their quotient lies in the kernel. So a trivial kernel forces distinct elements to map distinctly and conversely. So let's look at that more rigorously. So for step one, let's break this down into steps. We were given multiple parts, right? So we want to look at first that kernel phi, the kernel of phi is a subgroup. Check if that's the case. So our conditions, non-empty / has the identity. I can't think of a case in which something is non-empty but doesn't have the identity in this fashion, but there's likely something out there. Okay, so phi of 1 sub g is equal to 1 sub h, so the identity of g is equal, so phi of the identity of g is equal to the identity of h, right? So so the identity of g is within the kernel of phi. Now, for closure, if a comma b is contained within the kernel of phi, then phi of ab, well, that's equal to phi of a times phi of b, which is equal to the identity of h times the identity of h, which is equal to the identity of h. So AB is within the kernel of phi. So we have closure. Now, how about inverses? Well, for inverses, if A is contained within the kernel of phi, then phi of the inverse of A is equal to the inverse of phi of A, which is equal to the inverse of the identity of H, which is equal to the identity of H. So A inverse is contained within the kernel of phi. So the kernel of phi is a subgroup of G. Pretty cool. Now let's move on to the next part. The next step. So for step 2, we want to show if phi is injective, then the kernel of phi is equal to the identity of G. So that's one way. So it says if and only if, right? So we're going to go one way and then we're going to go the next way, the other way on step 3. But for now, let's just stick to this step. So suppose A is within the kernel of phi. Then what we can say is, okay, so phi of A is equal to the identity of H, which is contained in phi of the identity of G. Yes. Okay, so injectivity gives A is equal to 1 sub G, the identity of G. So the kernel of phi is equal to the set containing the identity of G. All right, now we want to go the other way, right? So let's go the other way. So if kernel of phi is equal to singleton set containing the identity of G, then phi is injective. That's what we want to find. Okay, so let's suppose here. Let's suppose phi of x is equal to phi of y. Okay? Then the identity of h is equal to phi of x times phi times the inverse of phi of y, which is equal to phi of x inverse y. Okay, so x inverse y is contained within the kernel of phi, which is equal to the identity of G. So x is equal to y, ergo phi is injective. Okay, now what can we conclude? Well, we can then say the kernel is a subgroup of G, and phi is injective if and only if the kernel of phi is equal to the singleton set containing the identity of G. All right, let's proceed to exercise 15. Okay, so proceeding to exercise 15, we have here define. Just 1 second. Define a map pi from the real numbers squared, so 2 dimensions, real numbers with degree 2 to real numbers with degree 1 by pi of open parentheses x comma y close parentheses is equal to x. And for this also we have prove that pi is a homomorphism and find the kernel of pi. All right, this is sort of continued from exercise 14 in a way, but let's just keep it self-contained. So intuitively, on the additive the additive group over the real numbers with degree 2 and the additive group over the real numbers with degree r, with degree n, addition is coordinate-wise, right? So projecting to the first coordinate clearly respects addition. The kernel should be all vectors whose first coordinate is 0, right? So let's go on to show that a bit more rigorously. So for this first part, we just want to see whether or not this thing is a homomorphism. So for open parentheses x sub 1 comma y sub 1 close parentheses comma open parentheses x sub 2 comma y sub 2 close parentheses, within the real numbers with degree 2, we have that pi of open parentheses x sub 1 comma y sub 1 close parentheses plus open parentheses x sub 2 comma y sub 2 close parentheses, that is in fact equal to phi of x sub 1 plus x sub 2 comma y sub 1 plus y sub 2, and that this is equal to pi of x sub 1 comma y sub 1 plus pi of x sub 2 comma y sub 2. So pi is a group homomorphism is a group homomorphism from the additive group over the reals with degree 2 to the addition on the reals with degree 1, right? So let's move on to the next part, which is the kernel. All right, so for the kernel, okay, so by definition, the kernel of pi, that's equal to the set containing coordinates x comma y within the reals with degree 2, such that pi of x comma y is equal to 0. And this is equal to the set containing x comma y within the reals with degree 2, such that x is equal to 0, which is equal to the set containing 0 comma y within the reals with degree 2, such that y is contained within R, the reals. So in conclusion, let's conclude here. Pi is a homomorphism. And the kernel of pi is equal to the set containing coordinates 0 comma y within the real numbers of degree 2, such that y is within the real numbers. Right? There we go. That's exercise 15. Now let's move on to exercise 16. So for exercise 16, let A and B be groups, and let G be their direct product, which we'll represent with A cross B. Prove that the maps pi sub 1 from G to A and pi sub 2 from G to B, defined by pi sub 1 of A comma B is equal to A, and pi sub 2 of A comma B is equal to B are homomorphisms. And find their kernels. Right? So intuitively, multiplication in A cross B is coordinate-wise, right? So projecting to a coordinate respects multiplication automatically. The kernel of a projection is everything with that coordinate equal to the identity. So let's go ahead and look at that a bit more rigorously. Start with the homomorphic part. Homomorphism checks for each of them. So for open parentheses A comma B, close parentheses comma, open parentheses C comma D for CD, for A comma B and C comma D within A cross B, pi sub 1 of open parentheses A comma B times C comma D, open parentheses A comma B, close parentheses, open parentheses C comma D, close parentheses. That's equal to pi sub 1 of AC comma BD, which is equal to pi sub 1 of A comma B times pi sub 1 C comma D. So pi sub 1 is a homomorphism. But there's more to say on that. Of course, we haven't covered pi sub 2. So let's get into that. So pi sub 2 of open parentheses A comma B close parentheses open parentheses C comma D close parentheses, well, that's equal to pi sub 2 of AC comma BD, and that is equal to pi sub 2 of A comma B times pi sub 2 of C comma D. So pi sub 2 is a homomorphism. All right? Now let's look at the kernels. Colonel Sanders. Okay, so for the kernels here, by definition, kernel of pi sub 1, what is that equal to? That's equal to the set containing open parentheses A comma B close parentheses contained within A cross B, such that pi sub 1 of A comma B is equal to 1A, the identity 1 sub A, which is the identity of A, which is equal to the set containing open parentheses the identity of A comma B. Yes, such that B is contained within B. Now, how about kernel 2? So for kernel pi over pi sub 2, well, that's equal to the set containing A comma B within A cross B, such that pi sub 2 of A comma B is equal to the identity of B. And that is equal to the set containing open parentheses A comma identity of B close parentheses, such that B is within, A is contained within A. A is an element of A. Little a is an element of big A, right? So, can we then say, well, each pi is a subgroup, each kernel is a subgroup of A cross B. This is by exercise 14, which we discussed that kernels are subgroups, right? So what do we conclude? Well, we conclude, for one, pi sub 1 and pi sub 2 are homomorphisms. And the kernel of pi sub 1 is equal to the set containing open parentheses identity of A comma B, such that B is an element of B. And the kernel of pi sub 2 is equal to the set containing open parentheses A comma identity of B close parentheses, such that A is an element of A. And that's it for exercise 16. Let's proceed to exercise 17. So let let G be any group. Prove that the map from G to itself, defined by G to its inverse, is a homomorphism. If and only if G is abelian, right? Okay, now let's go on here. Well, let's think about this intuitively. The inversion map reverses multiplication. So, open parentheses, AB, close parentheses, -1, that's equal to B to the -1 times A to the -1, right? So it will be a homomorphism exactly when reversing order does nothing. That is when A to the -1 times B to the -1 is equal to B to the -1 times A to the -1. Okay? For all AB. Equivalently, of course, AB is equal to BA, right? So that's what we want. Now let's look at this a bit more rigorously. Iteratively, a mix of iteratively and rigorously. Rigorously. Okay, so let's start with the first arrow of implication. So let's go left to right. And we want to see that if G is abelian, this is easier. If G is abelian, inversion is a homomorphism. Okay, so let's assume then that AB is equal to BA for all A comma B contained within G. Then for any A comma B, we have that open parentheses AB, close parentheses to the -1 is equal to B to the -1 times A to the -1, and that itself is equal to A to the -1 times B to the -1. So the map iota from G to G with iota of G equal to G of -1, which I'm putting the I dot there, but just bear with me here. So that map satisfies iota of AB is equal to iota of A times iota of B. And therefore is a homomorphism. All right? Now let's look at the other way. Okay, so we want to see that if inversion is a homomorphism, then G is abelian. That's what we want to see. We want to see the other implication, the right-left implication, right? So let's assume iota. I'm never not going to write the little tittle. Is that, I don't know, what is it? What is it that Christ says? Not one iota or tittle or something. I can't remember. But this little mark right here is a homomorphism. Every dot or something. That's what he says. I can't remember. I'll have to look again. Okay, so assume that iota is a homomorphism. Then for any A, B, and G, we have that iota AB is equal to open parentheses AB close parentheses to the negative 1, which is equal to b to the negative 1 times a to the negative 1, and that this is equal to iota of a times iota of b, which is actually equal to a to the negative 1 times b to the negative 1. And taking inverses of both sides gives AB is equal to open parentheses a to the negative 1, b to the negative 1, close parentheses to the negative 1, which is equal to BA, right? So G is abelian. What can we conclude from all of this? Well, we can say iota of G is equal to G inverse is a homomorphism. If and only if G is abelian. Okay? Now let's proceed to exercise 18. All right. So for exercise 18, let G be a group, be any group actually, be any group. Prove that the map from G to itself, defined by G to G squared, is a homomorphism if and only if G is abelian. So it's the same thing, it's just we're looking at G squared, right? So squaring G. So intuitively, a map is a homomorphism if it respects products in this case. So, well, the operation in general, but products in this case. So for G to G squared means what? It means open parentheses AB, close parentheses squared is equal to A squared, B squared for all AB. But open parentheses AB, close parentheses squared is equal to AB, AB. So the condition becomes AB, AB is equal to AA, BB, which forces AB to equal to BA, right? So conversely, if G is abelian, then we want open parentheses AB, close parentheses squared to equal A squared, B squared. We want that to hold automatically, right? So let's look at that a bit more rigorously. So let's go the first way, left to right. If the map from G to G squared is a homomorphism, then G is abelian. That's what we want. Let's assume some function psi of G is equal to G squared, satisfies psi of AB is equal to psi of A times psi of B for all A or B within G. Then open parentheses AB close parentheses squared is equal to psi of AB, which is equal to psi of A times psi of B, which is equal to A squared times B squared. Now, but open parentheses AB close parentheses squared is equal to AB. So AB is equal to AABB. Left multiply by the inverse of A, and right multiply by the inverse of B. And what does that get you? Well, let's okay. To get BAB is equal to ABBA, which we take that and we get BA is equal to AB. Now, let me erase the board so I can continue. Okay, so since A and B were arbitrarily chosen, or arbitrary, G is abelian, right? Okay, now let's look at the second part, the second implication from right to left. So, I want to show if G is abelian, then G to G squared is a homomorphism. Now, if AB is equal to BA for all AB, then psi of AB is equal to open parentheses AB close parentheses squared, which is equal to AB times AB, which is equal to AABB, which is equal to A squared B squared, which is equal to psi of A times psi of B. So, psi is a homomorphism. All right? So let me just say, so we conclude map from G to G squared is a homomorphism if and only if G is abelian. Right? Okay. Now let's move on to the next exercise, exercise 19. Okay, so for exercise 19, let G be equal to the set containing Z within the complex numbers, such that Z to the n is equal to 1 for some n within the positive integers, okay? And we want to prove that for any fixed integer k, bigger than 1, greater than 1, the map from G to G defined by Z to the map Z to Z to the K is a surjective homomorphism but not an isomorphism. It is not an isomorphism. Okay? So intuitively, G is a group of all complex roots of unity under multiplication. The kth power map respects multiplication automatically. Surjectivity holds because every root of unity has a kth root, which is again a root of unity. Just increase the order by a factor of k. Non-isomorphism. Okay, so all kth roots of unity map to 1. So the kernel is non-trivial when k is greater than 1. Okay, so let's look at that a bit more rigorously. Okay, so first part, homomorphism. So for Z, W within G, we have open parentheses Z, W, close parentheses K, which is equal to Z to the K times W to the K. So Z to Z to the K is a group homomorphism. G to G, right? That's supposed to be a G. So that works. The operation holds. Ergo it works. So now let's move on to surjectivity. Surjectivity, well, what I stated was very rough, but let's just move on to surjectivity. So oh boy. I'm going to define something different here from my notes. Let theta be an element of G, then theta is equal to e to the 2 pi I m divided by n for some integers m comma n, with n being greater than or equal to 1. Let's set sigma equal to e to the 2 pi I m divided by k times n. Well, then sigma is an element of G. It's so it's a k-nth root of unity. So what then? Well, then sigma to the k is equal to e to the 2 pi I times m divided by n, which is just equal to theta. So every element of G has a preimage. So the map is surjective. Which is what that means, right? So it's surjective. Okay, now let's move on to proving that it's not an isomorphism. I mean, we could just say it's not. Okay, so it's surjective. It's like, well, it's not injective, right? But let's go ahead and say not an isomorphism. That's what we want to prove. Non-trivial kernel. Okay, so not supposed to. Okay, all right. So the kernel is the set containing Z within G such that Z to the K is equal to 1. And this is actually equal to, let's say, mu sub K. The set of kth roots, we'll need that encapsulation here in a bit, kth roots of unity, which has k being greater than 1 elements. So the homomorphism is not injective. And therefore not an isomorphism. So what do we conclude then from this? Well, we conclude that the map from Z to Z to the K is surjective, is a surjective homomorphism. Which maps G to G, but not an isomorphism. With K being greater than 1. Okay? So let's move on to exercise 20 now. So for exercise 20, let G be a group, and let the automorphism of G, aught of G, be the set of all isomorphisms from G onto G, and let's prove that aught of G is a group under function composition. Called the automorphism group. Of G. Oops. And the elements of aught of G are called automorphisms of G. Okay. Right. So automorphisms are the symmetries, roughly speaking, of G. Composition of bijective homomorphisms is again a bijective homomorphism. So the identity map is an automorphism. Inverses of automorphisms are automorphisms. Those are exactly the group axioms, right? So let's get into looking at that a bit more rigorously. So let's start off with closure under composition. So if phi and psi are contained within aught of G, the automorphism group of G, I'll just say aught of G from now on, then both are bijective. Both are bijective homomorphisms. Homomorphisms which map G to G. The composition psi of phi is a homomorphism. And a bijection. So the composition is So psi of phi is an automorphism. Therefore, psi of phi is contained within aught of G. Now, let's try and search for associativity. Let's try and determine associativity. All right, prove associativity. So associativity. So function composition is associative. How do I know that? Well, we've already proved that. So for all alpha, beta, gamma, then so for all alpha, beta, gamma, a map from G to G, in a map from G to G, we have open parentheses alpha composed with beta, close parentheses composed with gamma, is equal to alpha composed with open parentheses beta composed with gamma, close parentheses. Oops, that's not quite what I wanted. So yes, it is associative. Now, let's get into the identity element. Check that out. So let's see. The identity map of G from G to G is a bijective homomorphism. So the ID of G, the identity of G, is contained within the aught of G. And for any phi contained within aught of G, we have that the identity of G composed with phi is equal to phi, which is equal to phi composed with the identity of G. So we have ourselves an identity. Now let's check inverses. All right, let's check inverses. Okay, so for inverses, if phi is within aught of G, then phi is a bijection. With inverse map phi of phi to the negative 1, the inverse of phi from G to G. Now, since phi is a homomorphism, its inverse is also a homomorphism. So, well, more directly, for x, y contained within G, we have phi of the inverse of phi of x, y, that is equal to x, y, which is equal to phi of the inverse of phi of x times the inverse of phi of y, which implies that phi, the inverse of phi of x, y is equal to the inverse of phi of x times the inverse of phi times y. So the inverse of phi is contained within aught G. Okay? Now, oh goodness. My making this a pincushion may not have been the best idea, but let's go on to discuss this further. So, moreover, phi of phi inverse composed with phi inverse is equal to the identity of G, which is equal to phi to the negative 1 composed with phi. All group axioms hold. From earlier, all group axioms, and with the inclusion of stuff that we did earlier, all group axioms hold. Therefore, ought of G is a group under composition. Under composition. So to conclude, ought of G is a group under composition. The automorphism group of G, right? Okay, so that's it for exercise 20. Let's move on to exercise 21 now. Okay, so for exercise 21, prove that for each fixed non-zero K within the rationals, the map from the rationals to itself, defined by Q to K Q, is an automorphism of the rationals. So intuitively, we view the rationals as the additive group. So like addition over the rationals, multiplying by a fixed rational, K, which is not equal to 0, clearly respects addition, distributivity, right? So, and is bijective with inverse multiplication by 1 over K. Let's take a look at that a bit more rigorously, though. So, for this, so first of all, let's look at the homomorphism part. So define phi to be the map from the rationals to the rationals. And do this by phi of Q, which is equal to KQ, with fixed K. It's an element of the rationals with the exclusion of 0, which is the units of the rationals, aka fixed, fix a non-zero K in the rational numbers. Oopsies, numbers. Now, for all A, B contained within the rationals, phi of A plus B is equal to K times open parentheses A plus B, which is equal, close parentheses, which is equal to K A plus KB, which is equal to phi of A plus phi of B. So phi is a group homomorphism from the additive from addition over the rationals. So addition over the rationals to addition over the rationals. Okay, now let's take a look at bijectivity. Okay, so for bijectivity, let me just put this down. Let's start with surjectivity first. Surjectivity. So given y is contained within the rationals, take x actually. X is equal to y divided by k contained within the rationals. Since k cannot equal 0 and 1 over k must be within the rationals. Then what do we have? Then phi of x is equal to y, which, we have surjectivity then. So, okay, now let's look at injectivity. Actually, let me erase and then switch the markers out. This one's going dry at this rate. Okay, I only got 2 left on here, so, but we can use the bigger one just in case. So, for injectivity, if phi of A is equal to phi of B, then k times A equals k times B. So A equals B, and this is because, of course, k does not equal 0. Since phi is a bijective homomorphism, because we established surjectivity and injectivity, since phi is a bijective homomorphism, it maps to itself, it is an automorphism of the additive group Q, addition over the rationals. So the inverse of phi is multiplication, by 1 over k contained within the rationals. Okay? Oh, we didn't really need that last part. We already kind of knew this last part, but, that just, it's a nice little thing to top it off with. But, so to conclude, for every k within the units of the rationals, addition over the rationals maps to addition over the rationals via q plus kq is an automorphism. All right, now let's move on to 22. Gotta finish 26 and then we'll call it. How much time do we have left? We'll see. Don't really want to make this into a 3-parter, but I will if I have to. So let A be an abelian group. And fix some k within the integers. So prove that the map from a to the k is a homomorphism from a to itself. So if, okay, and if k is equal to -1, prove that this homomorphism is an isomorphism. That is to say, is an automorphism of A. Right? So intuitively, in an abelian group, elements commute, so powers distribute over products. So open parentheses a, b, close parentheses k is equal to a to the k, b to the k for any integer k, right? So for k is equal to 1, this is the inversion map from a to the -1, which is its own inverse and hence a bijective homomorphism. But let's look at this a bit more rigorously. Okay, so for the first part, homomorphism for a fixed k within the integers. So let's let phi be a map from A to A, be defined by phi of A is equal to A to the k for all, equal to A to the k. And we'll move to this next part here and say that for all A and B within A or B within A, if k is greater than 0, then open parentheses A, B, close parentheses to the k is equal to open parentheses A, B, close parentheses, open parentheses, A, B, close parentheses, all the way up to open parentheses, A, B, close parentheses, with k factors. That is equal to A to the k times B to the k. Now, if k is less than 0, then write k is equal to -m, with m being greater than 0, then open parentheses A, B, close parentheses to the k is equal to open parentheses A, B, close parentheses to the -m, which is equal to open parentheses, A, B, close parentheses to the -1, close parentheses to the m, which is equal to open parentheses B to the -1 times A to the -1, close parentheses to the m, which is equal to B to the -m times A to the -m, which is equal to A to the -m times B to the -m, which is equal to A to the k times B to the k. So what can we then say? Well, so in either case, phi of AB is equal to phi of A times phi of B. Therefore, phi is a homomorphism. All right? Now let's go on to the next part, in which we'll look at the specific case in which k is equal to -1. So the case in which k is equal to -1, want to have phi as an automorphism. So when k is equal to 1, is equal to -1, phi of a is equal to a to the -1. It's equal to its inverse. So it's equal to the inverse of a. We already have phi is a homomorphism. Because A, capital A, is abelian. Moreover, phi is bijective with inverse equal to itself. Such that, well, the inverse of phi is equal to phi because open parentheses a to the -1, close parentheses to the -1 is equal to a. So phi is an automorphism. Right? So to conclude, a to the k is a homomorphism. On any abelian group A. And for k is equal to -1, it's an automorphism. All right, so that's 22 out of the way. So it looks like I'm going to have to make this a two-parter, a three-parter, I mean to say, because we are just about out of time for this room. But that is it for now. We'll pick up with the next one here in a bit.